What if I told you there's a way to solve some really complex coding problems in a single pass, using almost zero memory? Now, it's not magic. It's a fundamental skill that, honestly, a lot of developers overlook. Today, we're going to unlock bit manipulation, a true hidden superpower for any software engineer. Okay, let's just dive right in with a classic coding interview question. You're given a list of numbers. Every single number has a twin, except for one lone wolf. Your job? Find that unique number. Now, you could use a hash map to count them up, or maybe you could sort the array. But those take up extra memory or time. The real challenge here is to do it in one single pass using basically no extra memory. So how would you do it? Well, the most elegant, most mind-bendingly efficient solution doesn't use any of those common tools. The answer, our secret weapon, is bit manipulation. And I promise, by the end of this, you'll know exactly how to solve this and a whole bunch of other problems using this exact same technique. First things first, we need a whole new mental model. We're going to stop thinking about numbers like 5, 10, 12, and we're going to start seeing them for what they really are down at the hardware level. Just a series of lights. This right here is the single most important idea you need to grasp. Every number you've ever worked with is, under the hood, just a row of switches. The number 5, it's just a specific pattern of lights being on and off. Once you start seeing numbers this way, everything else just clicks into place. So if our numbers are just these rows of lights, how do we actually mess with them? Well, we have a core toolkit of operators that give us really precise control. Let's meet our first tool, shall we? First up, we've got the bitwise AND. This one's pretty simple, and it's also very strict. When you AND two numbers together, you're looking at each light in the same position, one by one. The light in your final answer will only be on if the lights in both of the original numbers were also on. If even one of them is off, the result is off. Simple as that. Let's see this in action. It makes it way clearer. So you take the number 10, in binary that's 0101, and the number 12, which is 01100. Now we go bit by bit. For the result to have a 1, an on light, both input bits have to be 1. As you can see, only one column, the fourth one from the right, actually meets that rule. So 10 and 12 gives us 0100, which is the number 8. All right, let's grab our next tool, bitwise OR. This one is way more generous than AND. For the results light to be on, you just need the light in that position to be on in at least one of the numbers. So if it's on in the first number or the second or even both, the result light is on. Okay, using our same numbers, 10 and 12, let's see what happens with OR. Now, a light in our result is going to be on if the light was on in either of the originals. So 01010 or 01100 gives us 01110, which is the number 14. You can see we're pretty much just merging all the on lights together. Now for the most interesting one, the operator that has some really special, almost magical properties. This is bitwise XOR, which stands for exclusive OR. The rule here is simple but powerful. The result light is on only if the input lights are different. So one on and one off gives you on, but two on lights or two off lights, that gives you off. Remember this one. It is the key to that puzzle from the beginning. Let's see XOR with our friends 10 and 12. Look at the bits on the far right. 0 and 0 are the same, so we get 0. Next up, 1 and 0 are different, so we get a 1. Then 0 and 1, also different, so we get another 1. The last two pairs, 1 and 0 and 0, are both the same, so they both give us a 0. The final result is 00110, or the number 6. It's just a test for difference. And finally, we have bit shifting. This is exactly what it sounds like. Imagine just sliding that entire row of lights to the left or to the right. A left shift moves every bit one spot over to the left. And you know what that does? It doubles the number. A right shift slides everything to the right, which cuts it in half. This is a ridiculously fast way to multiply or divide by powers of 2. Okay, so we've got our tools, AND, OR, XOR, and the shifts. Now, let's get to the fun part. Let's see how these simple little operations can be combined to create some classic, super powerful, and incredibly efficient programming tricks. This is probably one of the most famous bit tricks out there, so let's break it down. You take any number, let's call it x. We've got 12 here, which is 1100. Now just subtract 1 from it.
11 is 1101. Look closely at what happened. Subtracting 1 flipped the lowest on light to off, and then it flipped all the lights to the right of it to on. So when you AND these two numbers, that flipping action guarantees that the lowest on light from the original number gets turned off. 1100 becomes 1000.
So, why is that x and x minus 1 trick so cool? Well, think about what powers of 2 look like in binary. 2 is 10. 4 is 100. 8 is 1000. See the pattern? They all have exactly one on light. So what happens if you use our trick on a power of 2? Well, since there's only one on light to begin with, clearing it turns the whole number to 0. And just like that, you have a lightning-fast way to check if any number is a power of 2. And here's the ultimate payoff. All of these tricks, they're what we call O of 1, or constant time operations. What that means is the time it takes the computer to do them doesn't change, whether the number is 8 or 8 times trillion. Inside the CPU, these are basically single instructions. This is the absolute peak of performance you can get. Now, with great power comes great responsibility. Bit manipulation is absolutely amazing, but there are a few tricky spots and language-specific details that can really trip you up if you're not careful. So let's cover the big ones.
A huge source of bugs, for sure, is how right shifts handle negative numbers. There are two main flavors. The first is an arithmetic shift, which is what most languages like Python and Java use by default. This one preserves the sign. If the number is negative, it fills the empty spaces on the left with ones to keep it negative. But then there's the logical shift, which always fills with zeros. This can accidentally turn a negative number into a giant positive one. You have to know which one your language uses.
And there are a few other language-specific gotchas to watch for. In C or C++, if you try to shift by too many places, it's called undefined behavior, which is a programmer's worst nightmare. It might crash, it might do nothing, who knows. Python is a lot safer, it'll just give you an error. Also, keep an eye out for integer overflow. In C++, a number can actually wrap around from positive to negative, whereas Python's integers will just get as big as they need to. All right, we've gone through the theory, we've learned the tricks, and we've covered the pitfalls. Let's just do a quick recap of the key takeaways to really lock in these new skills. So what are the most important things to walk away with? First, always visualize numbers as those rows of lights. Second, get really comfortable with your core toolkit and/or XOR and shifts. Third, burn that x and x minus 1 trick into your memory. And finally, always be aware of those little language-specific traps, especially the right shifts on negative numbers. You do all that, and you'll be able to leverage the incredible speed of these operations. And now, let's go all the way back to where we started, that interview question. The secret, the whole key, was XOR. Remember how XORing a number with itself always results in 0? Well, if you XOR every single number in that list together, every pair of identical numbers will cancel each other out and become 0. The only number that doesn't get canceled is the one without a pair. It just gets XORed with a bunch of zeros, which leaves it completely unchanged. And just like that, you have your answer in one pass. You now have the toolkit, and more importantly, the mindset to see problems in a brand new light. And this isn't just for weird interview questions. It's used all the time in graphics, and networking, and databases, and high-performance computing. So the real question is, now that you have this superpower, what are you going to optimize first?